universal construction back to the work of Blanche, Heiberger, Nussbaum, and Vagel from 1995. There's also similar construction due to Friedman, Kitaev, Nayak, Slinger, Land, Walker, Wang on universal pairings and related work, follow-up work. And also, interestingly, Kapranov, I noticed recently that Kapranov mentions universal construction in his paper from 1995 about analogy between TQFTs and the Langlands program. Just mentioned that there's probably something along the lines that's probably too hard to say something in general, which is certainly true. So let me move on to the definition of this construction. So it's in spirit of TQFTs, but just slightly different. So we're going to work over a commutative ring, but most of the time we're going to work over a field K. And in this construction, so it's something really very simple to describe. We start with, we choose dimension n, and we choose some kind of n-dimensional objects. So they could be oriented closed manifolds. They could be manifolds with decorations by submanifolds and decorations by something else. So they could be forms or something of that kind. And then we start with numerical data. We start with an evaluation, a map alpha from diffeomorphism classes of this n-dimensional closed objects into the ground commutative ring R or a field K. So to every n, we assign alpha of n, an element of R. So in prime example would be assign such a number to any closed oriented smooth n-dimensional manifolds. And we require that this is multiplicative. So alpha of the disjoint union is the product of alphas. So then you just need to know alpha. Then all you do, you just choose an evaluation, a number for every connected closed n manifold, and that's it. That's your data. The diffeomorphic manifold should have evaluate to the same number. And so this is very general. So given such alpha, given such map, we can build something like a topological theory for cobordisms between n-dimensional manifolds or n-dimensional objects. And namely, so here just a remark that if you want to keep track of orientations, you can add involution so that alpha of the m with reversed orientation is the involution applied to alpha m, but we'll mostly ignore this because in low dimensions, we'll work with orientable manifolds. Reversing orientation results in a diffeomorphic manifold, so we'll ignore this involution psi or assume that it's identity. So back to n-1 dimension. So given a closed oriented n-1 manifold n, so let us first form the free R module with a basis all possible n-dimensional manifolds m with boundary n. So we have a homeomorphism between the boundary of m to n, just everything that n bounds. And on this free R module, we introduce by linear pairing, we take two. So this is just a symbol, kind of label, bracket n, just denotes m. So the bilinear form on this basis vectors, it's given by, so take m1, m2, glue them together. I mean, the reverse orientation, if we keep track of orientations of one of them, glue them together along n, we get a closed n-dimensional manifold. We can evaluate it using alpha to a number, to an element of the ground ring of field. So we have a system of these evaluations. So we can now define the state space of n-1 dimensional manifold n as this quotient, free module free of n on this basis of cobordisms that bound n module of the kernel with bilinear form. And of course, if you choose evaluations generically, randomly, then it's going to be a trivial kernel. So you'll not get anything interesting. You'll get this huge space with a basis of all cobordisms that bound n. But occasionally you get degenerations. So occasionally you get collapse. So in general, it has infinite rank over R, but sometimes you can get interesting examples with finite rank. This was a picture. Take M1, M2, reflect M1, and glue along common boundary N to a closed manifold, evaluate, get a coefficient, get a number. And so this theory, it's immediately from its definition, it has some triviality, because if you have a cobordism M from N0 to N1, n-dimensional cobordism, then you automatically get a map, symbol of M, from the state space of N0 into the state space of N1, and namely, this map takes an element, the symbol of M null, and manifold that bounds N null, dm null is null. Just compose it with M to take the symbol of M null. So just the most naive composition. And this respects the bilinear form, so takes kernel to kernel, so it induces a map on state spaces from alpha N null to alpha N1. And in this way, we get a functor from the category of n cobordisms between n-1 manifolds to R modules. And again, there are many variations because instead of manifolds, you can take manifolds with submanifolds, manifolds with decorations, forms, etc. And one thing about this functor, it's not monoidal. But what we have is that if you take two n-1 manifolds, n null and n1, so each of them say bounds m null m1, and then with m null m1 define vectors in alpha n null and alpha n1 correspondingly. And now we can just take the disjoint union of these cobordisms, these manifolds, and get a manifold with boundary union n null and n1. And this, of course, respects the bilinear form. So we get induced map from a state space of n null tensor state space of n1 into state space of n null union n1. And most of the time, good examples I know, this map is injective. It's always injective when the ground ring is a field, but it's usually not surjective. It's usually it's only injective because usually if you have a manifold which bounds the union of a null and n1, you may not be able to cut it into sum of pieces that separate about a null and one. And this relates to the question that Matt asks last time in Victor Stock. You usually don't have this neck cutting property that I symbolically wrote as that we cannot usually compose a tube. The tube is this cobordism, and manifold with boundary n union minus n. So just take identity cobordism on n and just turn around to get this tube. So this m doesn't decompose into such a sum usually in these situations. So these are xi's, yi's, they're just symbolic dots, meaning it could be some linear combination of manifolds you put in. So usually, usually there's no neck cutting. I want to point out in the standard, in the classical framework of ATIA of TQFTs, we do have neck cutting because in this classical framework, the map gamma on the state spaces is an isomorphism. This is one of the axioms. The state space of a disjoint union is the tensor product of state spaces. But this is not so in this case. And if occasionally it works, and then we say that alpha is multiplicative, call it maybe n-1 multiplicative. So alpha of the disjoint union is the tensor product of alphas on the level of state spaces. And this is n-1 multiplicative. And we always require multiplicativity on the previous level. So the invariant, the numbers we assign are multiplicative, but usually not vector spaces, usually not state spaces for n-1 manifolds. So let us look at an example, and this is very similar to Victor's talk from yesterday. Let us take n equal to 2 oriented manifolds. Then it breaks, and every manifold breaks into connected components. Every component is determined up to diffeomorphism by its genus, greater than or equal to 0. So let me call it S sub G, connected closed manifold surface of genus G. To it, we assign a number alpha of S sub G. I call it alpha sub G, an element of the ground field K. Let's use field for simplicity. So we have this sequence. All we have is a sequence of numbers, elements of field alpha null, invariant of a two-sphere alpha 1, invariant of a torus alpha 2 for genus 2, and so on. And we can put them together into a generating function z alpha variable t, this expression, which we can also write like this. And this is what we given, and out of this we can define state spaces. So what are state space for a single circle? State spaces are for n-1 manifolds, so for one manifolds, for a collection of circles. So if you have a single circle, all we can do is attach to it a surface of some genus with one connected component. So I draw the corresponding vectors here. V0, V1, V2. It's all the surfaces of genus N with one connected component. So we call them B sub N. So how do we get the state space? It's a quotient of this infinite dimensional vector space with this basis V sub N by this bilinear form. So the bilinear form takes Vn, Vm, we put them together, we get a closed surface of genus N plus M. And we apply, our evaluation to the surface. So we get alpha, we get the number alpha N plus M. So the inner product, the Gram matrix has ij coefficient alpha I plus j. So we can put this together into semi-infinite matrix, where at the intersection of in the ith row and jth column, we have alpha I plus j. So just a collection of these numbers. So you see that they go diagonally, alpha null, alpha 1, alpha 2, etc. And these are well known as Hankin matrices. They're used a lot in analysis. For us, so they appear as Gram matrices of the theory. And of course, what we want to do, so our state space for a single circle is this state space with the basis VI's or VN's for all n, but modulo the kernel of this bilinear form. And of course, if you just pick numbers randomly, you'll have trivial kernel and you have infinite dimensional space. But we want to look at the cases which are finite dimensional. And this means that we want the kernel of the bilinear form to be of finite codimension. And so the theorem here that Victor talked about yesterday, and I'll repeat, is that so the theorem says that so dimension of the state space of a circle is finite dimensional, the state space of a circle is finite dimensional, if and only if the state spaces for any number of circles are finite dimensional. And then if and only if the generating function z is a polynomial, is a rational function, polynomial p divided by polynomial q. And essentially this is due to Kronecker, we're just rephrasing it in this fancy way of topological theories. And between 1 and 2, it's not hard to go, because if you have one tells you that kind of you start adding handles, start with V0, a disk, V1, V2, Vr. Eventually, this must span your state space, and that means that R+1 handles will be a linear combination of cobordisms with fewer handles, with at most R handles. So you have a skein relation or a handle relation, saying that R+1 handles can be simplified to something smaller. And then you'll see a reverse of this expression as the denominator of this rational function. And we'll talk more about this later. Let me just mention then, once you know A1, you're not done, because A2, the state space for two circles, is potentially bigger than A1 tensor A1. Of course, you can, if you take element in A1 tensor A1, you can just put these cobordisms together, you get an element of A2. But potentially, there are also these tubes or tubes of some genus that are not expressible as sums of products of elements, of two elements of A1. Of course, if A1 is finite dimensional, then once you have enough handles, you can reduce this. So then in this case, you only get at most finitely many more dimensions, because you have a tube and some number of handles, at most are handles. And the same for all M. As you add the number of circles, you can create more complicated, you can create spheres with more boundary components that put them as boundaries of some of this collection of M circles. And you can add handles, but you can only add up to R handles, and beyond that you can reduce. So you can easily see that the state space is finite dimensional for all A of M. Once you know it's finite dimensional for A1. So this direction is very easy. And let us work out an example where, where our generating function z is just a constant. So there are no high terms, just a constant beta, and non-zero element of the field. For simplicity, we assume characteristic is 0. So this is what it looks like. So evaluation is beta on the 2 sphere, and on anything else it's 0. And in particular, you have a very simple handle relation. The handle relation says that a handle is 0, because if you have a handle, then no matter how you're going to glue it, no matter what you're going to put on the other side, you're going to have a surface of genus at least 1, and it evaluates to 0. So you know that in the state space of A1, a handle punctured torus is 0. And in particular, you know that A1 has just one-dimensional. It's just spanned by the disk. Disk is non-trivial because if you couple it also to a disk, you get beta. It's non-zero, so that vector is non-trivial. But then anything else you see in A1 is 0. All the higher genus surfaces are 0. Okay, so A1 is one-dimensional. Now, what about A2? Well, in A2, we have to restrict to surfaces such that every component has genus 0, no handles, because otherwise it's 0. So for A2, we can get 2 pictures. We can get a tube and we can get 2 disks. And to check if it's, and that spans, because there's nothing else, everything else is 0. So to check if it's a basis, we should write down the Gram matrix. So we put these 2 vectors here, and we put these 2 vectors here, and then couple them to each other, reflecting one of them. This is what it looks like: 2 spheres, 2 sphere, 2 sphere, a torus. So we evaluate. This is beta square, 2 spheres. This is beta, beta. This is 0. Determinant is minus beta square, not equal to 0. So indeed, it's no relation. So it's a basis. For A3, you can do you can do some computation. You have 5 possibilities that correspond to set theoretic partitions of number 3. All the ways to break 3 into union of subsets, disjoint subsets, 1 for every connected component of a diagram. So just 5 possibilities. You can check if the determinant is 2 beta squared, 2 beta to the 5th. So computation, 5 by 5 matrix. Since we impose characteristic equals 0, this is invertible, and it's indeed a basis. And then you can play the same game beyond dimension 3, and eventually it starts. Eventually, you need a computer. And I think in this whole business, it's extremely useful to run things on the computer for testing. But in this case, you can actually still do by hand. In this case, reducing to genus 0, you look at Cartesians of 4. You have 4 boundary components, say 15 elements. You can check if there is one relation. You can look for relations that are invariant under the action of a symmetric group S4, because S4 acts by permutations on the circles. So you can just look for such relations. There are a few parameters. So I wrote down the relation that we can find. So there are 8 terms, only 8 terms out of 15. The other 7 don't appear. And so, for instance, with 3 terms, they start with this term and add all the permutations under the action of S4. And likewise here. So we get this term. We can use it, for instance, to express this component with 4 boundary circles as a combination of other components. But we also notice, for instance, that out of these 8 pictures, one of them is special. And this is special because it has a crossing. So it has a crossing. You have 2 tubes. If you decide to put them inside the free space, they're gonna intersect. And this relation allows us to reduce this crossing to something that has no crossings. You have surfaces that we drew inside the plane, inside the free space, but their components don't intersect. So we can think of this as crossingless surfaces. And again, this relation means that no matter what you put on top, no matter which cobordism or which surface you glue on top, the same one for all 8 terms, evaluate, you get 0. That's what the relation means. Okay, but so this relation allows us to reduce such crossings to fewer crossings, to no crossings. The remaining 7 terms have no crossings. So we can reduce to a spanning set. So in this state space A(n) of n circles, we can reduce to a spanning set of what we call crossingless surfaces. What are crossing surfaces? So the genus, the surfaces are such that every component has genus 0. And they're in bijection with crossingless matchings of two endpoints on the line. This is how the bijection goes. So here, so you put two endpoints on the horizontal line on the plane, and we choose a crossingless matching of these two endpoints by arcs in the lower half plane. Now we shade in checkerboard fashion. Outer region is white and shaded, and white and shaded if there is more, and so on and so forth. So we can do the shading, and then we go to free space and we thicken shaded parts to handle bodies, sort of, well, handle bodies, maybe just spheres, and then so this is the picture. Without trying to perfectly define it, I just show you a picture. So you kind of thicken so that every interval between consecutive points, every shaded interval, it thickens to a circle in the free space. And then every connected shaded region thickens to a sphere with holes. And this you can formalize to bijection between crossingless matchings of two endpoints and crossingless surfaces, bounding and circles. And so the theorem that we prove, so this is Yakov, joint with Yakov and Victor. So if the characteristic of the field is 0, then the state space for this particular function, it's a very special function, the constant function, beta. The state space for this particular theory for n circles has dimension Catalan number, and it has a basis of crossingless surfaces. If you choose prime characteristic, then eventually crossing the surfaces become a spanning set. So there are too many, not a basis. And the proof is based on a determinant computed by Yakov from our paper joint with Yakov and Nito Kichlo in progress. The paper is about forms, but somehow we end up the same. In a special case, we get the same determinant. Which was interesting. That's one way to prove it. Another is relating to representations of OSP1, 2. So Ina told us in details just now about representations of OSP1, 2. So it also makes an appearance here. So you can, I don't know if when we were writing the paper, we couldn't really find good references, detailed reference for OSP1, 2 and diagrammatics of its representations. There are some papers on OSP1, 2n, but we didn't see really something as detailed about OSP1, 2 as say you can find for SL2 or quantum SL2. So I think there's maybe some kind of gap in the literature, at least in the textbook literature, that would be nice to feel, just kind of develop diagrammatics for OSP1, 2 and its quantum deformation as detailed as we had for SL2 for a long time. But you can relate this category to representations of OSP1, 2. So that's one example. Now, what happens in general, and again, I'm gonna kind of repeat what Victor said yesterday. In general case, you have a two polynomials, numerator and denominator of your generating function of some degrees. Unfortunately, I use the same notation for, at the beginning, we used NM for manifolds. Now I use for degrees, I'm sorry. So let degrees of P and Q be NM, and let K be the max of n plus 1 and m. So here there's kind of a separate cases when the fraction is proper and when it's not proper. In the denominator, we can normalize so that Q of 0 is 1. And then if this is the denominator, then this kind of handle relation we discussed before is just given by reading these coefficients backwards. So what you do is you need this kind of, so again, you can show that this theory is rational if and only if coefficients are recurrent, or sometimes you can call it eventually recurrent. But if you have this formula starting from some possibly large lowercase n, but alpha, the coefficient evaluation of genus n plus m surface, is a linear combination of evaluations of surfaces of lower genus with these fixed coefficients b's, and these are exactly the coefficients of denominator, but in reverse, because as we decrease alpha, index of alpha here, we increase beta, but here if you go from top to bottom, the index will be decreased. It's exactly the reverse polynomial, but you need to add something in general. So the point is that if the degree of numerator is strictly less than the degree of denominator, then you just have this, recurrent property from the start for all the coefficients, starting with alpha sub m. But if the degree, if the ratio is not proper, so if you can write p over q as p tilde over q plus some polynomial r of t, or this is not proper, then you have some, so informally speaking, random. The first few alphas could be random. They can carry stuff from r of t, and because of this recurrent relation will only start at some point, because coefficients of r of t, so to speak, add garbage or add noise to the sequence. So you only have it eventually. But if fraction is proper, then you have it from the start. And so you can check then that the handled relation has the following form. It's the reverse polynomial of q of t, but you need to multiply by power of x because you don't always start from the beginning. And you multiply it by the power of x, which is the difference of k, so the max n plus 1 and m. For proper fractions, this term vanishes, just 1, but otherwise you multiply by power of x. And this is our handled relation. So it says that once you have k handles on your component, you can reduce to fewer handles using these coefficients from the denominator function. So we can call it handled polynomial, handled relation. And then in the state space of A1, a state space of surfaces with which bound one circle, we have a basis of powers of the handle called handle x. We have a basis of powers of the handle up to xk minus 1 to the handle. And this A of 1 is it has a structure of a commutative Frobenius algebra on one generator. So it's kind of not that much choice. The multiplication comes from Penn's cobordism. Excuse me, because you can take two cobordisms with boundary circle and merge them using Penn's into cobordism with boundary circle. So you have multiplication, and it has a usual Frobenius structure from the trace, and this is a basis. One example: if you take this function z, you see that it's not proper because the degree of numerator is the same as the denominator. So in this Kane relation, in Kane relation, you'll have an extra x. So we take, I'm not sure if that's exactly one of the examples that Victor gave. I think he gave a similar example. So we take these coefficients, we write them backwards. So now 2 is in the lowest degree, and we need to multiply by x because the fraction is not proper. And this is our handled relation. And so our Frobenius algebra for one circle has very concrete form. You can play around, you can use idempotence in this algebra to simplify things. We do some of that on the paper, but we didn't fully kind of use the idempotent decomposition, but to some degree. And I won't say that that's not everything, because this inclusion, for instance, is only an inclusion usually. So you have more terms. You can have this tube that doesn't come from here, and you can add some genus to it. For A3, you have more. So there's a little bit more than just a single Frobenius algebra on one generator. And I will point out that we found out that there's extensive literature on this recurrent sequences. So sequences of this form. There's lots of interesting results. There's a whole book written on it. So this is the reference. The whole book written on recurrent sequences in fields or in number fields. They're used in applications in some the design of chips. So they kind of, I think it's some simple way to get sequences that kind of sort of quasi random sequences. I mean, they can have very long periods even if they have low degree polynomial. And so now the name for them is linear recurrent sequences. I wrote down an example of interesting theorem that we learned while writing this paper. I don't know if this theorem can be has some interpretation using topological theories, cobordism, but it would be interesting to explore. This is an example of Skolem-Mahler Ledge theorem. Says that in characteristic 0, if you take a recurrent sequence, if you look at its zeros, all the n such that alpha n is 0, and it's always a union of finite set and finite remaining arithmetic progressions. It's sort of not surprising, but it's a nice result, and it's easy to see that it fails in characteristic P for infinite fields. Just some kind of use standard game with powers of P will give you a counterexample. And so you can find many long discussion of recurrent sequences in this book on finite fields, and also refer to the book by Gersler Eisenhower on recurrent sequences and much more along the lines of what we're discussing.
So we're about half an hour in, and we can take a break whenever it's convenient. Yeah. Okay, so feel free to ask questions.
Yeah, I had a question. So, yeah, so in the example that you gave, where the dimension of these state spaces were Catalan numbers, you also have like an action of the symmetric group on. Sorry, what am I trying to say? So this looks like obviously something related to temporal-Levy algebras. Can you say more directly what is it?
Yes, I think, I mean, as I understand, and maybe if Victor or Vera are participating, we can say more. So this is not SLQ. This is OSP12, and OSP12 it has its fundamental representation. It's very similar. As I understand, it's very similar to the three-dimensional representation of SLQ, because if you look at the spaces of invariance of tens of powers of the representation, they have the same dimension as corresponding invariance of tens of powers of VQ, where by VQ I mean the three-dimensional irreducible representation of SLQ. So there is a quality in dimensions, but the graphical calculi are different. But again, I haven't seen a nice presentation of the graphical calculus for OSP12, kind of similar in detail as we've done for SLQ many years ago. I mean, I did something like that in my thesis for SLQ and for SLQ. But OSP12, I mean, there are some papers on OSP12 and etc. But they kind of, it would be nice to have something in great detail, similar to, for instance, books by Kaufman-Linz or Hofstetter. But I mean, it's somehow, I think it's some gap in the literature that would be nice to fill, just for kind of service purposes, so we can all use it. So I think there is similarity, but it's not quite SLQ. Cross-inverse matchings, well, it's again, it's this representation. It's this representation of OSP12. But to get the state space of a circle, I mean, as I understand, the unlock would be to take this representation and add it with trivial representation, and then you get a Frobenius commutative Frobenius algebra object in the category of OSP12 representations, and that object is analogous to simpler kind of more elementary object that we see in SLQ and quantum SLQ. In SLQ, we can just take V, fundamental representation tensor V dual. And this has a structure. This has a very simple structure of Frobenius algebra because you can just merge V with V dual. You can just use arcs to connect V with V dual. So it has a simple structure of Frobenius algebra. And in OSP12, I think it's a little bit different. And in OSP12, I'm not sure if you can take square root using some thickening of OSP12. If you can take square root of three-dimensional representation plus trivial, similar to what we do for SLQ, where we take V plus the dual, actually isomorphic to itself, and that the product is trivial plus 3 dimension. I'm not sure if maybe I'm going very fast. I'm sorry. I don't know if that all makes sense. But so it's sort of, it's very similar. It's very similar to SLQ, and in Innerstock we saw that it's actually very important for the algebra. But definitely kind of details of the story are missing, but you can probably find even more general papers on OSP12.
Can I just make sure I understood? So if I take like the nth tensor, so if I take n disjoint circles and look at its endomorphism algebra in this category?
Yes.
This is some, are you saying that this algebra is sort of isomorphic to the endomorphism algebra of the nth tensor power of some OSP12 representation?
Yeah, yes. So I think what we can say is that forms from the trivial, from the kind of empty, from no circles to n circles are going to be isomorphic to the space of invariants in the nth tensor power of the four-dimensional representation of OSP12. And that four-dimensional representation is the trivial representation plus the fundamental three-dimensional or 1/2 dimensional representation of OSP12. And that's, as I understand it, I learned this from Victor, and I think Victor also learned this from Bera and from Noah Snyder. And we have difficulty finding really good references for all of this.
Okay, cool.
But also sort of, I mean, you can also ask Victor and ask Vera and Noah and Inna to understand. But I agree, it sort of seems to be, it hasn't been written down very carefully, apparently. But it's worth writing down.
Interesting.
All right. I think we can continue whenever you're ready.
Okay, great. So let's move on to, so here we discussed the state spaces. So far discussed state spaces on circles, but you can also can say this on a more categorical level. And for this, so again, so we really be down to earth. We just have our cobordisms, bilinear forms, numbers, gram matrices. That's incredibly down to earth. If you go to tensor, if you look at the level of tensor categories, so in tensor categories, as we done from many talks in this conference and many other resources, there's a very useful notion of modding out by negligible morphisms. And just a reminder, so I'm going to skip the kind of necessary words like rigid, linear, etc. So in negligible morphism, so you take a morphism F between tensor products of objects in the category, and you say, I draw it schematically as this blob, and you say it's negligible if no matter how you close it, and here I schematically close it using morphism G, no matter how you close it, then the closure is an endomorphism of the identity object. You want all the closures to be 0, no matter what G you put. And if that's the case, you say that F is negligible. And so such this kind of, so it's sort of, it's 0 if you look at F as part of a closed network, no matter which network. So it's kind of invisible from the closed network viewpoint. So then we say that F is negligible, and inside the tensor category, we have ideal J of negligible morphisms. It's a two-sided ideal because if something is negligible, it's not visible via closed cobordisms, but no matter what you attach to it, the result is still not visible. So it's still negligible. So it's indeed an ideal tensor, two-sided ideal. So this is the standard reference for tensor categories, and you'll find discussion of negligible ideals there. So let me just call it, kind of decide to call it negligible quotient, just to avoid the long, just let's say quotient of the category by the ideal of negligible morphisms. That's very long, so let's call it negligible quotient, the C modulo J, quotient category by negligible morphisms. And so it turns out that there's quite subtle questions. I don't know about this recently, but questions like, when is this quotient semi-simple? And so I want to say that, I mean, you can kind of start with a tensor category and build this quotient, but also in the universal construction, you don't have a tensor category, you just have a variation, you have this collection of numbers. And then out of universal construction, you can build this quotient C. It's the analog of modding out by kernel, which is saying that if given a cobordism or combination, if no matter what you attach to it is 0, the result, this should not be visible. This is in the kernel. It's exactly the same as saying that F is negligible. No matter how you close F into a closed object, it should evaluate to 0. So it's parallel. And then working with categories, of course, it's very useful to take additive Karoubi closure. So let us see how this works in the universal case in dimension 2. This is based on a joint paper with Admiral Sazdanovich. So I think it's very, very natural to gradually build up these categories to see what's going on. And we're going to start with a rational series alpha. So that state spaces are of n circles are one-dimensional. And so here we start at the beginning, just category on the far left, category COP2 of two-dimensional oriented cobordisms. So objects are numbers n, for every object n there is n circles, objects and morphisms and cobordisms. So we go slowly, step by step. So first we keep the same objects and we linearize morphisms. So we take formal linear combinations of morphisms with coefficients in the field K. So next step, we call it viewable cobordisms, but just use whatever word you like. Viewable cobordisms, that's why viewable means that now if you have a cobordism, it might have a component that's closed. For instance, this component is closed, has no boundary. It's not viewable. Then we evaluate this component's closed components via evaluation alpha to numbers in our field. And then in this category, forms between collections of circles are linear combinations of viewable cobordisms which have no closed components. Okay, but in this step here, it's still Hom spaces are still infinite dimensional because you can have any number of handles on a component. So at the next step, we go to this scan category, maybe it can be called handle category. So as cobordisms, we sort of look at the relations where cobordisms have boundaries here and -1 sphere, in this case a circle. All the relations on cobordisms with boundary a circle and add these relations. And we just add the handle relation u of x equal to 0, where we can compute u as the reverse polynomial of q times some power of x if necessary. And in this category here, the nice thing about it is that once alpha is rational, in this category, and we have no trivial relation, in this category, Hom spaces are finite dimensional because you have some number of circles upstairs, downstairs. You have a partition of the set of circles by connected components. And then it has some genus, but genus is bounded because of handle relation. And because of this, the Hom spaces in this category are finite dimensional. And then in all the other categories we're going to build in the square, Hom spaces are finite dimensional, which simplifies our life. And still, the objects are just natural numbers, 0, 1, 2, etc. Just one object for every collection number of circles. So what can we do? We can kind of fully commit ourselves in this downward arrow, take negligible quotient. And here it means that we not just mod out by the handle relation, by the relation for cobordisms that bound the single circle, but by all the relations. We take the quotient. Let us call this cob alpha, this negligible quotient. So we're killing all negligible morphisms, but it's also the same as what we did at the very beginning. Namely, we just take, so in this category cob alpha, the space of Homs from the empty one manifold to n circles is exactly our state space an of n circles from the beginning of the lecture. So we eventually get to this universal construction doing the steps, but the steps are convenient. Again, objects are natural numbers, and we can take a different direction from the scan category. We can pass to the additive Karoubi closure, and that means we allow formal finite linear combinations, formal finite sums of objects, and then also add idempotence. So take Karoubi closure. And we get a Karoubi complete category, which is the analog of the Delin category. So if you take generating function z, which has the form a constant divided by a linear function, you recover the Delin category. And in fact, this relation between the Delin category and partition category and cobordisms was first noticed by Jonathan Thomas, kind of building up on his idea. And once you pass from partitions to cobordisms, you see more parameters. You see the genus of a cobordism. But so this is kind of, we like to think about this. So from a scan category, we can pass to this Karoubi closed category, which is the analog of the Delin category, or we can pass to the negligible quotient. And from a Delin category, we can take the negligible quotient of a Delin category. We get d cob alpha underlined, and it's as equivalent to going this way, the first taking negligible quotient and then taking additive Karoubi closure. And this square commutes in a strong sense. In a sense, we get this category in two possible ways, going this way and going this way, because the Hom spaces are finite dimensional. So if you were working over a cumulative ring in auto field, you would have to do more work to understand what happens. So this is a special nice case. And sort of the kind of classical example, if the dealing category would be S cob alpha would be the partition category. I think D cob alpha is a dealing category, and D cob alpha underlined is the quotient of the dealing category, the negligible quotient. And so this is, I think this is a kind of very useful way to think about what's going on in this collection of categories. And I want to say that in follow-up work, you see versions of these categories, versions of this diagram, but with just different categories, but it's very, very similar construction. This is the path you follow. And always once you get to here, to scan category, you're kind of careful to have finite dimensional form spaces. So then after this, whether you take Karoubi closure or whether you take negligible quotient and do either in either of the two sequences, you end up with the same answer in the bottom right. And I think in high dimensions, it should get more complicated once you add more defects. Once in high dimensions, this is only going to be harder. But we kind of don't really know anything about dimension 3. Of course, beyond whatever we can borrow from TQFTs. Okay, so let us move on. Let's go one dimension down. Let us maybe go one dimension down. But here you actually get another interesting story. But so you go one dimension down, but we want to decorate. So it's Christmas time, so we want to add decorations to our one-dimensional cobordisms. So we choose a set S of labels, and we look at one manifolds, but with dots. So codimension 1 defects or 0 manifolds on them, and we label every dot by an element of a set S. And you can set up a corresponding category of cobordisms. And if I have a picture here, I think I actually don't have a picture of morphism in this category here. You just oriented one manifolds with dots, and dots are labeled by elements of a set S. Then we have a lot of flexibility, a lot of freedom and parameters in the variations, because now we have a component that is a circle with dots. We can read off the labels as 1 is to Sn. We get a sequence of elements of S, and now evaluation alpha depends on the sequence. And for every sequence, we get an element of K. And here, because we are in a circle, the sequence is symmetric in the sense that if we evaluate the evaluation on the product of sequences AB is the same as the evaluation on the product of sequences BA. So there is symmetricity or central series. And again, this goes back to this kind of power series, go back to Schutzenberger, Friis, Eisenhower, going back to the 1960s. So what you do, so you have lots and lots of parameters, and you can encode them into this power series where variables are non-commutative. So this power series Z alpha, we take the sum of all sequences of elements of S, coefficient or evaluation alpha of W times W. So W here is the sequence S1 Sn. And we take the sum of all sequences, so it's a power series in non-commuting variables. So elements of S are the variables, and they don't commute. So the series is symmetric, and this example, if you have a very large sequence, there are lots of ways to permute it, not cyclically. So here I'm kind of rushing because we have 10 minutes left. Rushing, so you use this non-commutative algebra of non-commutative polynomials in variables S, and you put it inside the algebra of non-commutative power series, this infinite series. And then you repeat the same game. So you can build state spaces. Now state spaces, well, we keep orientations, we keep track of orientations. So when we to build a state space, we need to have this one manifold. So we need the same number of plus and minus signs. Plus and minus signs are orientations of 0 manifolds, of ends of our cobordism. So you can just say that we have n pluses and minuses, and then for n pluses and minuses, you can consider the state space of n arcs that carry all possible dots, and you can define a body uniform, carry all possible decorations by dots. You can define a body uniform. So in this picture, we use dots A and B as a two-element set. So this is an example. We have a collection of n arcs here, a collection of n arcs there. We couple of them, if we evaluate them, we get a circle and a circle. So it's alpha of a square b times alpha of a b a square b cubed in K. And so this is how we build the state space. Just take all this, that's kind of, it grows exponentially. But so they take this vectors, take this giant Gram matrix of the biuniform and mod out by the kernel. And so in fact, so you get something that's close to well-studied structures. So you get, if you look at this quotient for n equal to 1, when you have just a single plus and single minus point, so you have just a single arc with dots. Then the corresponding quotient is known as the syntactic algebra u to root an hour, AF1. So you would quotient polynomials in non-commutative variables by the syntactic ideal of negligible elements J, such that no matter what you put here and close up, this evaluates to 0. So it's a syntactic ideal. With an algebra this way, it has multiplication. This is a picture for multiplication. And just want to mention that the series here, again, they're sort of, it's anything goes because they're non-commutative series, non-commutative variables. But here they are symmetric, so they're invariant under this rotation. But if you want, you can easily modify this to any series. Instead of circles, you allow one manifolds with boundaries. So if you have one manifold with boundary, if you have an interval, you can put dots on the interval, and then now there's no rotation. Now every sequence is on its own. It evaluates to some alpha, and for rotated sequence, the outputs are different. So it's very easy to have this construction to allow for non-symmetric power series. You just have cobordisms that will have that can also end in the middle. Can have us floating endpoints. The two types of endpoints: the boundary endpoints and the endpoints inside the cobordism. And then the theorem. So we're stating classical theorem, which says and kind of this topological restatement would say that dimension of the state space A1 is finite if and only if dimension of any AN state is finite. If and only if it's rational. You just have to say what rational means for the series, and this is a classical subject in the foundations of computer science. This is a canonical reference, book by Bernstein and Riotenauer. And so the notion, so a rational series is the following. So it's a smaller subspace of non-commuting power series, which contains all non-commutative polynomials. That's linear. That's closed on multiplication. So when you multiply, it's fine. It's still a power series, and you need to add all the inverses. So if you have a series Z, which has 0 coefficient, which has kind of 0 of return, alpha of the empty sequence is 0, then you can form this infinite sum. It's still a sequence, because in this infinite sum of powers of Z to the n is only non-zero when you evaluate it on terms of length n, at least. And so this is a well-defined power series, and you can think of it as 1 over 1 minus Z minus 1. So you should add, you kind of inductively build the space, requiring that it's also with any Z of this form, it contains this expression, this sum. And this, interesting enough, and this has origins in automata theory that goes back to Quine, Isenberg, and other finders, Schutzenberger, where you have this notion of a regular language that kind of a basic topic in computer science can be described using, it's a language that is seen by finite state automata. And then this regular language, if you just write the expression, the infinite sum of all the elements in the language, you get a non-commuting power series, except that it's a series not over a field or a ring, but it's a series over Boolean semi-ring, where you have just 0, 1, and 1 plus 1 is 1. So this theory of rational series, it works over a field, works over a ring, works for automata, for Boolean semi-ring, and people also do it for semi-rings, general semi-rings, and you get what's called weighted automata in this theory. So it's a very developed field. So we kind of, in the story, we sort of seeing, on one hand, we're seeing tensor envelopes of non-commuting power series, but potentially, I mean, this hasn't been explored at all, but potentially you can play around and maybe understand tensor envelopes of this finite automata or weighted automata. Again, I have no examples to offer, so, but it's worth a shot. So maybe it could be interesting. Look at these tensor envelopes in the nonlinear case when you have Boolean submarine or a field. And but so going back to the case of a field and rational Z alpha, and I mean there are more connections. I mean, people have studied this from the viewpoint of non-commutative geometry. I should mention canonical work by Kohn, Kansevich, Ginsburg. So it's Retach. So it's been studied a lot from as a possible direction for non-commutative geometry. But anyway, so back to a field and tensor envelopes, you can get a full analog of the category we wrote down before in the two-dimensional case. So you have a full analog of this category. Here, so for instance, here you'll see instead of the handle relation, you'll see the analog of the quotient by the handle relation is written our syntactic algebra. Then when you take negligible quotient, you potentially get more relations. And you can kind of variations, oriented, unoriented, one manifolds with boundaries. So there are variations of the story. And sort of interesting potential connections, including to computer science and other fields, but completely, I would say, completely unexplored. So you don't know how insignificant they are. And let me also mention, how much time do I have? 3 minutes. Let me also mention that this, you can think of it as kind of a Brouwer category, but with decorations. So Christmas time Brouwer category, where you, if you have no decorations, then you just have a circle and it validates to a number, and that's the parameter of your Brouwer category. But with decorations, you get much more flexibility. And so let me also mention joint work with Chi and Leo Prazansky, where we kind of play this game in 2 dimensions, but we look at sources with boundary. So we have top bound, so horizontal boundary, and we have side boundary. And that's more flexibility than in the closed surface case, when we have just genus 1 parameter. Here we have 2 parameters, because we can count, because every surface can have boundary on the sides. Kind of a closed object is just an object without top and bottom boundary, but it might have boundary components. So you get 2 parameters for closed connected objects. You get genus and a number of handles. And when you form the generating function, you get series in commuting variables T1, T2, T1 for number of components, T2 for handles. And here the straightforward theorem is that the state spaces are finite dimensional if this generating function has the form polynomial divided by polynomial in T1 and T2. So notice that we don't put just polynomial in T1, T2, it has to be separate. And that's exactly the case when the state spaces are finite dimensional. And I am out of time, so I should stop here. Let me can you say something? So when you match this, when you compare the situation with Moore-Siegel, who studied this sort of open close to TQFTs, and a later paper by Lado Pfeiffer and many others, so they see a Frobenius algebra and commutative Frobenius algebra related to the center of that Frobenius algebra. But we see only commutative Frobenius algebras on 2 generators, holes and handles, and that because we forgot to add decorations on the boundaries. We forgot to add decorations to the boundaries of these 2 decabordisms. So once you add decorations, then Frobenius algebras become non-commutative in general, and that gets a better match with Moore-Siegel and Lado Pfeiffer and this open-closed 2-dimensional TQFT story. And I'll finish with these questions. I'll just you can look at them, and I guess I should stop here. Thank you.
Thank you very much. Let's thank Mikhail for the nice talk. And feel free to ask questions.
And I want to say that kind of, I think this is just in its very early stages. So it's sort of in the stage of showing you the money in the sense it looks interesting, but it has yet to prove itself. It has yet to find significant connections to other science, to other parts of math. So to me, it's kind of, I think before, I'd like to see kind of deeper connections before saying, well, this is kind of really should be studied. But I like what we have so far, but I'm biased, of course.
So maybe I'll start with a question. So I know that somehow in link homology, it often plays a role that we consider TQFTs to be graded. And on cobordisms, somehow this is encoded by the Euler characteristic. How does the 2D theory that you described change if you take into account gradings?
Yeah, you can do the grading, but then most of the time you need to work over a ground ring. So for instance, in the theory for the constant function, you can keep track of the Euler characteristic, and this beta will have non-trivial degree, and you can do it, and so then your theory has that grading by beta and something you build out of Euler characteristic in a simple way, and then you just have to be more careful because over a ring of polynomials, in this case in beta, it's more complicated than over a field. You just have to be more careful with all of that. So we haven't done that in a paper. I can also refer you to the first paper on this matter, where you can take the polynomial p divided by q and assume that all the factors are linear. So p, all the factors of p and q are linear, and then you can put in parameters, one parameter for every linear factor, right? The p as product of 1 plus some parameters beta it, and denominator as product 1 minus gamma jt. And just use these betas and gammas or symmetric functions in them as your ground ring. And then interestingly, you can see a little bit of representation theory of this superalgebra GLNM. In particular, if you take this Hankel matrix and you take the minors of the matrix, choose some rows and columns, take the determinant, you'll see supersymmetric Schur functions. So Schur functions for GLNM as those determinants, which is interesting. And those theories will be over polynomial rings, symmetric functions in variables beta times symmetric functions in gamma, and you can keep track of degree as well.
Thanks.
Yeah, I have a question. Is it possible or reasonable to understand which initial data I give like a multiplicative TQFT, either in the sort of first, like in a 1 plus 1?
I think in the QD case, I think what Victor wrote down yesterday, it maybe answers this question, and I think that I think for multiplicative theories, I think you need to specialize to some kind of, it's very close to Victor, I think called semi-simple. So I think in that case, it's just probably just some kind of function t times some non-negative number n plus some of functions of form lambda I inverse divided by 1 minus lambda it, where lambda I is some coefficients you pick, some numbers you pick, maybe times some multiplicity and I think Victor wrote this formula in the super case if his coefficients were integers.
Mm-hmm.
But I think for just over vector spaces, you should take coefficients to be non-negative integers. Yeah, I'm not sure if we proved this, and of course it's going to be harder to understand in other examples when is the theory multiplicative. But sometimes you might be able to get multiplicativity by some kind of completion, just add more vectors, in the sense that if you take invariance in invariance in tensor products of quantum group representations. I mean, by itself, it's not multiplicative in the sense of invariance in the products of products are strictly bigger than invariance, than product of invariance. But you can just complete two tensor products. So there, in some cases, there might be some kind of simple ways to, or non-trivial ways to get to multiplicative theory by this sort of completion. But again, I kind of don't really know what those examples are. But definitely in the story we get from forms, so I think I mentioned in the last slide that in the story we get from forms, things are multiplicative, except in the case which we don't know are regenerated as L3 forms. There we don't know if the state spaces are multiplicative under disjoint union of trivalent graphs on the plane. And the first case when we don't know is when you take the tetrahedral graph, where we don't know whether this map from the homology of two copies of the tetrahedral graph into homology of the disjoint union is an isomorphism. So somehow that is very subtle. So we don't know the answer for the tetrahedral graph, but I refer you for results here, partial results here to David Boozer's paper. And there's some discussion in our recent paper with Adrien. And on the gauge theory side, there are 3 papers by Kanhan and Brovko on this story.
Thanks.
Yeah, and just briefly, I want to say that kind of in the story, kind of you see all the time that you kind of feel almost like you're doing something applied. And so conceptually, it's because you're in a situation where you have it, you know, the evaluations for closed objects, for manifolds, and you want to build, you understand what happens inside. You want to build the theory of the state spaces for n-1 dimensional objects. And this feels just like what people do, probably what people do in data science or in other applications where you have some data or you have input-output data, but you don't know what happens inside, and you want to build a model, preferably simple one, for what happens inside. So in this case, it feels very similar, and you kind of see kind of something like control theory appear, or this linear recursive sequences, finite state automata. It feels very close to applied science. Again, I don't want to make a distinction between pure and applied, but kind of there is this definite feeling that this way is kind of close to understanding the system from observations, from outside observations. And this is very informal.
All right. So if there are no more questions for the recorded part of this session, I suggest we thank Mikhail again.
Thank you.
And I will turn off the recording now. And so feel